Welcome everyone. In this video we're going to be talking about the entropy change for an irreversible adiabatic expansion. That's really the only type of process we haven't covered yet. Okay, so for an irreversible adiabatic expansion, right, we again know that entropy is defined, right, as dq reversible over T, okay? But in order to find, right, so if I do something for an irreversible process, right, in order to calculate the entropy, I need to find a reversible path that connects the same initial and final states. Okay? So doing an adiabatic expansion irreversibly, both temperature, pressure, and volume all change, right? My temperature, if my volume increases, my temperature and pressure decrease, right? For an adiabatic process, okay? And the temperature change for an irreversible expansion of a gas adiabatically and a reversible expansion of a gas adiabatically are not the same, okay? Because the work done is not the same, and the amount of temperature change that's required to do that expansion is related with the amount of work that's done, okay? And so I can't just imagine doing the same exact change in state adiabatically or reversibly, because it won't produce the same change in state if I do the same change in volume, okay? And so we need to create some other path that is a reversible path to get me to the same initial and final temperature, pressure, and volume, okay? And so how I'm going to need to do this is through some secondary state, right? I'm going to have to do two steps. I'm going to have to do reversible step 1 and reversible step 2. Where I have some intermediate state with some temperature, volume, and pressure that could be whatever they are, okay? So this is going to have to be a two-step reversible process to connect my irreversible state, right? I'm looking for the change in entropy between these two systems, right? But this is an irreversible change in entropy, right? To get that, I'm going to write this as a sum of reversible changes in entropy, right, of two different steps, okay? So one way we could do this is do a reversible isothermal expansion followed by a reversible constant volume heating, okay? So for the reversible isothermal expansion, right, reversible isothermal expansion, delta S is just NR ln V final over V initial, right? I'm expanding my gas from the same initial and final volumes that I did for the irreversible adiabatic expansion. And then for the reversible constant volume expansion, I just do N CVM ln T final over T initial, okay? Right? Where again, I'm going from the same kind of initial and final temperatures as I do from the irreversible adiabatic expansion. So the total entropy change is just given by this equation down here, the sum of those two quantities, okay? Now, because entropy is a state function, right, I can use this for any irreversible process where temperature, pressure, and volume all change. It doesn't have to be adiabatic. It just has to be some process where temperature, pressure, and volume all change, okay? And in that case, I could use this as a formula to calculate the entropy change for that process, okay? Now, you might ask, well, what if I picked a different path? Right? What if I did two different irreversible steps, right? What if I did a reversible adiabatic expansion from the same initial final volumes and then a reversible constant volume cooling, right? So I'm going to go from some initial temperature to some intermediate temperature through that reversible adiabatic expansion, and then I'm going to keep the volume the same and change my temperature from that intermediate temperature down to the final temperature that we want, okay? So, right, for that first step, we know that entropy changes to 0, right? For reversible adiabatic, entropy changes 0, and so the entropy change for this entire process is just that N CVM T final over T initial, where in this case T initial is that intermediate temperature I'm calling Tx, okay? Well, we know, right, for the reversible adiabatic expansion, that the final temperature of that expansion, which is Tx, is related with the ratio of the initial and final volumes to this NR divided by CV power. So if I plug in this expression into Tx here, right? That's what I'm doing here. And then we're just going to simplify it, okay? So first thing we can do is factor out T final over T initial, right? ln of x times y is just the ln of x plus the ln of y. So I have NCVM ln of T final over T initial plus NCVM ln of V final divided by V initial to the NR divided by CV. Well, I can just pull out that power in front, okay? And so I have the NCVM ln V final over V initial, pulling out that power gives me NR divided by CV times NCVM, okay, which, right, so here I'm putting CV, right, because NCVM is just equal to CV, okay, and so now I have this CV canceling with that CV, and I'm left with NR ln V final over V initial, okay, and then I have that first thing, which is, you know, NCVM or CV ln T final over T initial, okay, which is the exact same expression as the other path I picked. Okay. And I could do this exact same thing with doing a reversible constant pressure change and then a reversible constant volume change. Okay. Right, for the reversible constant pressure, my change entropy is NCP ln of Tx, that intermediate temperature, over Ti. And then a reversible constant volume process is going to be NCVM ln of T final divided by Tx. Okay. So the total entropy change is just the sum of these two quantities. So using that expression from the last slide, the first thing I'm going to do is I'm going to essentially in here, I'm going to multiply it by T initial over T initial. Okay. And so that's going to give me this T final over T initial times T initial over Tx. And I'm going to again use the properties of the natural log to make that NCVM ln T final over T initial plus NCVM ln T initial over Tx. I'm going to flip what's inside that ln and change this to a minus sign when I do that. And then I can combine the two terms here to have ln of Tx over T initial, okay, to give me NCPM minus NCVM ln Tx divided by Ti plus NCVM ln T final over T initial, okay, which this term here, right, for an ideal gas, right, is just equal to NR times ln Tx over Ti, okay, plus NCVM ln T final over T initial, okay, right. And so finally, right, we have to kind of get rid of this Tx here, right? So in that first step, I did a constant pressure expansion of an ideal gas, okay? Right? I know from my ideal gas law, right, that temperature initial divided by volume initial equals NR divided by P initial, which is also equal to the temperature final divided by volume final, okay? Right, from the ideal gas, right? If NR divided by P is staying constant because pressure is being kept constant, that means the ratios of the temperatures and the volumes are equal. And so I can get that Ti here divided by Tx is equals Vi over Vf. And so plugging that in to the above expression here, okay, I get the delta S is NR ln V final over V initial plus NCVM, or just writing that CV if you want, right, ln T final over T initial, which again is the same expression as all the other expressions, right? So no matter what path I pick, I will always get the same entropy change, okay? I just need to make sure I create a reversible path to connect my initial and final states if the problem isn't done reversible.